In this lecture, we will learn about reciprocal lattice. So as we see, it is a reciprocal of the lattice. So how does it evolve, and why is it essential? We will learn about in this particular lecture. To learn about diffraction, it is highly essential that we learn in terms of reciprocal lattice, and how does it evolve? We will talk about that in this particular lecture. We might be familiar already with the Bragg's equation, and we know that Bragg's equation is given by 2d sine theta is equal to n lambda. So taking that particular equivalence, we can directly see that if we keep our lambda as constant, our sine theta is inversely proportional to the interplanar spacing, which means that if I have a large atomic spacing, it will produce a smaller diffraction angle. So that's what we can see, that sine theta is inversely proportional to 1 by d. So as my lattice spacing increases, I get diffraction which is at much smaller angles, and also that the smaller atomic spacings will produce a larger diffraction angle. So that is the inverse relationship of the interplanar spacing with the diffraction angle. Secondly, we can also see that if we have for a particular lattice spacing, for interplanar spacing, I can also see that my sine theta is inversely proportional to my energy, or in other words, if I start increasing my lambda or I start decreasing my energy term, then obviously my theta also will start getting. If I start increasing my lambda, then my theta will basically decrease. So that's what is the equivalence what we can see here, because as my energy is higher, my lambda is lower, so eventually my theta also has to decrease. So for higher energy terms, I can see diffraction at much closer points, or theta is very low when I have very high energy wavelength. So I can see that the diffraction pattern will vary with the incident wave particle energy, and the diffraction angle, they become smaller once I increase my incident energy, or once I reduce my lambda. So my theta increases, my theta decreases as I decrease my lambda. So that is a direct dependence I can see with theta, in terms of energy or the wavelength. At the same time, if I keep my n as either plus 1 or minus 1, I can see that this law will be again valid, and it shows that there is some sort of symmetry which is basically which has to be incorporated for different values of n. So automatically diffraction is it will have the same probability whether my n is equal to plus 1 or n is equal to minus 1. So my diffraction pattern automatically inculcates some symmetry into itself. So just summarizing it, if I keep my lambda as constant, my sine theta and d have inverse proportionality, or in other words, if I have my d value as constant, I have a direct proportionality of theta and lambda. It means if I reduce my lambda or if I increase my energy, my theta value will be very low. So that tells where my diffraction spots will finally appear in terms of Bragg's equation. Secondly, the Bragg's law, it is not a positive law, it is a negative law, which means that if I am not satisfying Bragg's law, no diffraction will occur. But once my Bragg's equation is satisfied, I may see those diffraction, and diffraction is well defined as reinforced coherent scattering. So it is basically reinforcement of the coherent beams which are scattered. So that defines my diffraction as such. And again, Bragg's law, or 2d sine theta equal to n lambda, this particular equation is a negative law, and that tells me clearly that if I am not satisfying this particular equation, my reflection will not occur. But if this condition is satisfied, it may occur. That's what is being defined by the Bragg's law. And again, there are certain factors of scattering by various electrons, because initially we will have scattering by individual electron, that brings out the polarization factor. I can have the whole atom, because atom is consisting of so many electrons, it will have something called atomic scattering factor, and all those atoms will be now arranged or organized in a particular unit cell in certain fashion. So it will result out my unit cell structure factor. So I have polarization factor which evinces from the electron, or I have a whole atom which has many electrons. So this particular factor is dependent on my atomic number. Then I have the structure factor which is dependent on so many atoms which constitute or define a particular unit cell. So this is how my intensity basically varies. Then coming on to the next part of it, I see that my overall structure factor is not dependent only on the positions of my atoms which are there in the unit cell. So I can see that structure factor is independent of the shape and size of the unit cell. It just depends on the location or the positions of atoms and what their atomic scattering factor is. So that part we can clearly see from this particular part. The overall structure factor is not dependent only on the my Miller indices and the location of my atoms which are located out there in a unit cell. So it is independent of the shape and the size of unit cell. And again, it can have various intensities. The overall atomic scattering factor can be different for if I have two kinds of atoms, atom A and atom B. And what I will get finally is kind of a resultant amplitude which is arising from the scattering of different kinds of atoms. So overall, I can see that my overall scattering factor is dependent on only on the location of atoms in a particular unit cell, and it is independent of the size of the unit cell or its shape. And this thing also we might have already learnt about it in the X-ray diffraction, that all those reflections which may be present in a simple cubic, I have all the reflections which may be present. For a body centered, I have only H plus K plus L Miller indices, which the combination when it is even, I get my reflection. For face centered, I should have H, K and L which are unmixed. It means all H, K and L have to be all odd, or everything has to be even. And then for end centered, I need to have H and K unmixed for the C centered one. And for necessary absence reflections which are totally absent, for simple cubic, I should have everything like everything is present, so I don't have any reflection which are absent. Actually absent when I have H plus K plus L is equal to odd for BCC, and for FCC I have H plus K plus L, they are all mixed, so then I won't get any reflection. So these are all the criteria for a diamond for a DC, FCC, BCC or SC cells. Now coming back to which forms the basis of my of the reciprocal lattices. Like if I start seeing a particular crystal and I start defining each and every plane by their normals, so I can see the points begin at a fractional coordinate of 1. So this is what is defining my particular unit cell. So this is the end limits of a particular unit cell. It will have a dimensions of 1 on each side. But as soon as start coming into the particular crystal, I will see that I have the different planes, plane 200, plane 400, they all start falling from the outside to inside. Similarly, I will have all those points available here as well. I have 1, 1, 0. So I will have my 1 bar 1 0 somewhere here along the same side. I will have my 2 bar 1 0 somewhere here, 2 bar 1 0. And similarly, I will have more intensity of points along this side, which is near the origin point. So I will have more intensity of points which will start crowding my central location. So this problem is that we have increase in the intensity as we start approaching the origin. So this is my origin. As soon as I start coming, as soon as I start creating all the planes or labeling all the planes, I will have more intensity in the central part, because my 100 is at this particular part, this particular point, and 200 is at the half the distance. So I will have more agglomeration of points in this particular regime. So to basically come out from this particular problem, we define something called a reciprocal lattice. And the problem arises, say if we want to see a particular 100 plane, I orient my crystal in approximately with 100, and which has an equal angle with the beam as well as the detector. So I can define that my theta is basically obeyed, and I can obey the Bragg's law for a particular alignment. So this becomes very easy for 100 plane or lower index planes. But what happens if I want to go for a higher or complicated higher index plane such as 246? So basically it creates some problem or complexity once I want to visualize all those things in 2 dimensions. So actually what I have is 2D planes which have intersection of a 3D unit cell. So this creates much more complexity. So if you want to visualize this 246 plane, what I can do, I can just remove the 1 dimension of it. So once I can remove 1 dimension, I can see everything in 2 dimension, and that's what I am more comfortable with. So I can remove those 1 dimension from my unit cell, and what I see is everything in the reciprocal lattice spacing. I can see, I can form the same crystal in a reciprocal lattice I remove one dimension, now I have much more simpler view for analyzing. So I have everything, a representation of crystal itself in a reciprocal lattice, and I am removing my one dimension. Now I have the same plane with much more simplicity. And how do we go about that? It is more like this, that we have each set of parallel plane, and those parallel plane have length which is equal to the reciprocal of the interplanar spacing. So if I had a reciprocal lattice for a cubic unit cell, say if I had D111 is equal to A by my under root of h square plus k square plus l square for a cubic cell. So what I can do in my reciprocal space, my new spacing will become 1 by D111. So my D111 star will become 1 by D111. So I have this set of parallel planes of 111 which have their length equal to the reciprocal of the interplanar spacing, and the normal direction to this particular plane is the orientation of the corresponding set of parallel planes. So I can also define its orientation, I can also define its magnitude, what is the overall spacing between all those particular planes. So each point which is being observed in the reciprocal lattice, that is nothing but a parallel set of planes. So all the planes like 100, all the set of parallel planes which are shifted by a particular unit cell distance, all those I can represent by a single point. And now I know its direction because I will have the normal direction which is orientation of a corresponding set of parallel planes. I know its magnitude, that is nothing but the 1 by inverse of the interplanar spacing between those particular set of parallel planes. So I can define each point in the reciprocal space as a parallel set of planes. So what I was seeing here, that my 100 was here in the normal nomenclature, with 200 out here, 400 out here, but in terms of reciprocal lattice, my 100 is out here, my 200 is double the spacing, my 400 is 4 times the spacing of 100. So now I can see all this part, I am basically opening it up to go on the other side, and I can see my lattice much more clearly. So my 100 is here, 200 is out here, 400 out is here. So what I can see a uniform or periodic distribution of all those points, which I can define by either by its vector quantity. So now I have A star, which is nothing but a reciprocal lattice, and on this side I have a B star, and now I can see everything is now in a 2D. I have removed one dimension to it, which is nothing but the 001 part of it. I have already removed it, that becomes a zone axis, and I can present all my points, all my planes so nicely by a single point. Now I know my direction as well. I know my direction. This thing is my 100 direction, and that's what I am going here with. And this of my direction is 010. So that's where I am going, and it is perpendicular to the 001 one plane. So that's what I can see here. That becomes the zone axis. So now it becomes much more simpler for me to represent all the planes. I know their magnitude. What is the interplanar spacing? That becomes 1 by d of the interplanar spacing in the reciprocal lattice spacing. I know its direction. So I can represent now set of parallel planes by a single point in a reciprocal lattice. And the concept of reciprocal lattice comes more like this, that I have an incoming X-ray beam. It can again be a electron beam depending on kind of diffraction which is occurring. Then I have the evolved sphere. This is nothing but the evolved sphere, which has a radius of 1 by lambda, and upon interaction with the crystal, some beam gets transmitted, but those which are following which are obeying the Bragg's law, they get diffracted out here, and what I get is a diffraction spot on the evolved sphere. So this is my first spot which will come out here. This is my transmitted beam, and this particular distance is nothing but 1 by d, or the inverse of the interplanar spacing. So I have 2d sin theta is equal to n lambda. Now I can define this sin theta is equal to 1 by 2 times d divided by 1 by lambda. So I can see that if I take a particular thing like this, I can define that my incident beam interacts with the material crystal, goes away, then everything is falling on the evolved sphere. These two particular points I take A and B, I can take them A and B, and the half of it is my theta. What I am seeing is 1 by 2d. This is my 1 by lambda. So that's what is now being shown from this particular equation. So I have particular crystal planes which are oriented in certain direction. They give out my theta and 1 by lambda, and I can now see that everything is now falling on the evolved sphere, this particular part. So I can see this is my evolved sphere, and then I can, what I get is spacing of 1 by d out here. So that's what is being represented by the reciprocal lattice. So it means that all the points which are falling on the evolved sphere, all those points on the reciprocal lattice which are falling on the evolved sphere, only they are producing my diffraction spot, because they are the ones which are obeying the Bragg's law. Because we can see sin theta is equal to 1 by 2d whole divided by 1 by lambda. So I have my evolved sphere which is a radius of 1 by lambda, and also I am getting the theta value of 1 by 2d, or the 2 theta becomes 1 by d. So that's what I am seeing out here in the evolved sphere construction, that I have my 1 by d, I have my 2 theta out here, and that's what is giving me the diffraction spot. And again, this is what is being stated, that diffraction will occur only when a reciprocal lattice point touches the sphere. That is what is obeying, and then that will create a diffraction spot. So let this be the construction of a reciprocal space. So I have my reciprocal lattice. I have my reciprocal lattice out here, RL. This can be individual plane which can be represented by all this intersection of all those points. So I have my points. It's a 2D reciprocal lattice, so it's 2D to 0, 0, 1.0, 2.0, 3.0, and so on. So, and this is my evolved sphere, and this has a radius of 1 by lambda. Radius of 1 by lambda. So what I can see, this particular distance, it is touching the evolved sphere. This particular point is touching the evolved sphere. So I have 1 by d of 4, 1. This is again in 2D only, 2 dimension. So I am seeing that my evolved sphere, it has a radius of 1 by lambda, and I am getting 1 by d, which is of a particular plane, which is being satisfied by 4, 1 plane. So when the point is touching 4, 1, I am getting a diffraction spot. So my reciprocal lattice, once it coincides with the evolved sphere construction, I get a diffraction spot. So it is more like this. I am sending a beam. I have a crystal plane which is oriented at certain theta value, and once it obeys the theta value, I have theta 1, 1, 1, and again in this particular case I have theta 2, 2, 2. So once it is touching the evolved sphere, say if my my plane is exactly oriented, so I will get a diffraction spot out here. For plane D222, I will get a diffraction spot at some other point, because now my theta 22 is different than theta 111. And for a particular material, once I utilize a copper K alpha, I fix my lambda value, or my inverse of lambda, it comes out to be 0.65 per angstrom. In this case, I have units of 1 by length, because it's a inverse inverse construction of a particular length scale, and that eventually brings out my 1 by d value of around 0.43 per angstrom. And if you realize, if I calculate 1 by d222, it comes out to be approximately 0.86 per angstrom. So we will see that it is much more periodic in nature, and my this length is exactly half of my d22. So that's what brings the periodicity in this particular construction. So if I want to see it again as a merger of these two, I can see that I have plane 111, I have plane 222, and how do they can fall on the same evolved sphere, because my 1 by lambda term is constant for a particular radiation. And now I can see the plane 1111 has to be aligned differently as compared to the plane D222 to give me a diffraction spot. So I need to have kind of a polycrystal material with a proper orientation with my plane 111 and plane 222 to produce a diffraction spot at particular location in the evolved sphere. So my reciprocal lattice has to be such that it basically comes out or touches the evolved sphere, so that I need to have a polycrystalline material. So my reciprocal lattice will be accordingly to particular plane, and my evolved sphere is constant because my lambda value is fixed for that. So I can get diffraction spot at some location. So coming back to it, the direction and length of the reciprocal space, it will be more like this, that my DHKL plane is pointing from origin to the point. So this is origin and it is to a point. So this is a plane 110, and now this particular point is now perpendicular to the first family of HKL. So now I have plane 110. So the overall point towards it, or the DHKL pointing from origin to this particular point, will be my particular plane in the reciprocal lattice with its direction of D110. To construct a reciprocal lattice, my direction, so this be the normal lattice construction. So I have A1 vector and A2 vector which are in the real space, which is the length along A1 direction is A1. So in reciprocal space, I have this particular length which is A1, that becomes now 1 by A1 in my reciprocal lattice. So I had a length of unit 1 which becomes 1 by A1. So I had a length of A1 which becomes 1 by A1 in my reciprocal space. So this particular point which was A1 by 2, now that becomes 2 by A1. So I had this particular length, this becomes now 2 by A1, and so on. Similarly, A2, that becomes 1 by A2, something like this, this becomes 1 by A2. Any point out here in the center part, this particular length now becomes 2 by A2. So that's how the reciprocal lattice gets constructed. So I had this 1 1, this particular point, this now becomes this particular point. So if I had some 2 comma 2, that becomes basically out. So any point 2 comma 2 out here will now be at this particular location. So this particular point now has converted to this point. This point has now gone to this point. So that's how I construct my reciprocal lattice like this. One more condition to be noticed is that my new B1 vector is perpendicular to my A2 vector. So my reciprocal lattice vector of B1 is perpendicular to my A2 vector, and my B2 vector is perpendicular to A1 vector. So my reciprocal lattice, it has a unit vectors which are perpendicular to the my real space lattice vectors. So seeing it properly again, so we can have again this A1 and A2 which are the real space coordinates, real space vectors, and now my B1 will be now perpendicular to A2. So my B1 or the reciprocal lattice vector will be perpendicular to A2. So my perpendicular vector will come out approximately like this, and that is nothing but this particular plane. So that's what I am seeing, that 10 plane is now falling here, 20 is falling out here. For A1, it has become B1, and now B1 is perpendicular to A2, and now my B2 will be now like this in the reciprocal space. That's what I am seeing out here, that now B2 is perpendicular to A1. So that shows the perpendicularity of the various vector in the reciprocal lattice. So it is very essential that it is not only diminishing the dimensions by 1 by, it is also becoming perpendicular to the original other axis. So I had A1, so it is now helping the B2 to form, which is perpendicular to A1, and my B1 is perpendicular to A2. So that's how it becomes in the reciprocal lattice spacing. Or the basis vectors in 3 dimension can also be defined by the cross product of the other two. So my B1 star becomes the A2 cross A3 divided by V, where V is the volume, or B2 becomes the A3 cross A1 by V, and B3 becomes A1 cross A2 by V. And again, particular thing is, again B3 is again the reciprocal interplanar spacing, and again B3 will be perpendicular to both A1 and A2. That is how I can see that how the overall lattice reciprocal lattice spacing is being constructed. So I can see my B3, it will remain perpendicular to my A1 as well as A2, and this particular distance is nothing but 1 by the interplanar spacing of particular plane, which can be 0 1 1, or it can be something else as well. This will be 0 0 1 approximately here. So that is what is being shown out here, how I can construct my reciprocal lattice. So what I can get finally as the interplanar spacing is nothing but the my Miller indices plus the reciprocal lattice vectors. So that is how we will define my 1 by d of HKL, that is given by the lattice reciprocal lattice vector, which is again nothing but the corresponding to the real lattice plane. So I have this G vector corresponding to the 1 by d vector in the real space. And again this reciprocal lattice construction becomes the alternate way of representing my real space, real lattice. So that's what is the so good about reciprocal lattices. I am eliminating one dimension, at the same time I am able to mimic my real lattice. So that is how that's how it assists me visualizing things much more clearly. And again coming back to the relations of the reciprocal lattices, I can see that my A star B, A star C, or my reciprocal lattice spacing with the original BC, it becomes 0 or it is perpendicular to the original axis. Similarly, my B star, the dot product of my B star with A and C, it again brings 0, and again my C star with A and B, it brings out 0. It means everything is, all these things are perpendicular to the other two axes which have it formed. And again the reciprocal axes are the scalar products of the axis from the direct lattice. That's how it basically forms the reciprocal lattice. And this is nothing, the V volume is nothing but the A dot B cross C, or B dot C cross A, or C dot A cross B. That's how I get the volume of the direct lattice. And for a simple cubic lattice, I can see that if I take the dimensions to form a cube again, I'll have to go again one in I direction, one in J direction, and one in K direction, and that's how I get my reciprocal lattice parameters of A, B, and of A star, B star, and C star, all the three axes, to form a particular unit cell, where small a, this particular thing is nothing but my lattice parameter. So I get I by A, J by A, and K by A. Ideally 2 pi comes, this factor particularly comes because to maintain the periodicity of a particular structure. So it is converting it into more into the radiance part. So that's how it maintains as well the periodicity of the particular crystal in terms of taking it to the reciprocal lattice. So finally I get A star is equal to 2 pi A multiplied by I, B star is equal to 2 pi J by A, and C star is equal to 2 pi K by A. And now coming to the BCC lattice, this A is again my lattice constant for a cubic lattice, and again A, B, C are the new axes which will really form the new crystal. So to define a particular volume, I again take A dot B cross C, and it eventually comes out that my A star is equal to 2 pi by A I plus J, B star becomes 2 pi A J plus K, C star becomes 2 pi by A K plus I, and this ideal construction comes from the equality of my points which will form a particular unit cell. So I can see that from origin I have to go certain distances out here like this to 3 different cells to be able to form 3 axes of the new crystal or the new lattice which will form. So I can see for constructing particular for a particular axis, my A direction I have to go I minus J plus K whole by 2. For second thing, for B I have to go minus I plus J plus K, or for C I have to go I plus J minus K. So eventually doing this all those vector algebra or all the cross product, I can see that it eventually comes out I plus J, J plus K, and K plus I to form my final crystal or final lattice. Similarly for a FCC lattice, my 3 equivalent points basically are these particular points which are sitting on the 3 different faces. So those correspond to I plus J, J plus K, and K plus I. So I can see I have to traverse 1 in each direction, because this is my bottom face, this is my front face, and this is my side face, the center of that. So I can see that I have to travel I plus J by 2, J plus K by 2, and K plus I by 2, and taking the periodicity of 2 pi, I take my again the cross product of B cross C, and I divide it by volume. So I can get some parameters which are more like this. Eventually it turns out that the reciprocal lattice of BCC is equal to FCC. So I can see that this particular part is similar to what I had started with in a BCC. So I can see that this particular part and this particular part is now similar to my I minus j plus k. So it is basically I minus j plus k. It is similar to this particular part. So I can see that reciprocal lattice of FCC is equal to BCC and reciprocal lattice of BCC is equal to FCC. So that shows a correspondence or correlation from the BCC to a FCC lattice, that simple cubic remains a simple cubic, but my FCC becomes BCC in reciprocal lattice spacing, and then my FCC becomes BCC. So what I can see out here is that reciprocal lattice is the reciprocal of the primitive lattice, and it is purely geometrical. Since it is only geometrical, it is not dealing anyhow with the intensity point. So what I am getting particular point, it is just showing me that it is reciprocal lattice, or it is forming a reciprocal of the primitive lattice without taking care of the intensity of any particular point. So I can have some primitive cells, something with the non-primitive cells, but again how do I decorate them? It really depends on the location of my particular points. It might also happen that some reciprocal lattice points may go missing, or they can be scaled up, or they can be scaled down in the terms of intensity, or it can have a decoration of some motif, because depending on the scattering power. And again the evolved sphere construction can further select those points which are actually absorbed in a diffraction experiment. So it is again a probability that whether it will come or not, it totally depends on the scattering power of a particular plane or a particular element or particular atom which is being present there. So only the location and the scattering power itself, the combination of that decides whether a particular diffraction spot will be present or not. So the construction of evolved sphere plus the diffraction which is coming here, they jointly say whether a particular spot will be present or absent. So seeing it in a different manner, so I can see that in my diffraction, once the diffraction is occurring, my row spacing in the diffraction pattern has become 1 by d. So initially when I had an interplanar spacing of d, it becomes 1 by d in my reciprocal spacing. And again I can see this surface diffraction either in terms of rows of atoms and draw a kind of a qualitative picture of the diffraction pattern just by considering what kind of planes are present. So just by considering the space between those rows, I can construct my reciprocal lattice. So from that I can eventually bring out my diffraction pattern. So if I had a real space like this, where I have say for surface of FCC 110 plane, then I can see that in my FCC 100 plane, it becomes more like this. I have atoms which are associated at this particular location, as well on the face centers. So I have something on the faces as well. So I can get something more like this, and seeing their 100 particular plane, this particular plane, I can see that I have planes which are more like this. I will get some sort of a construction where these atoms are much more closer as compared to these particular atoms. So that is what we are seeing here, that in this particular case we have A is less than B. It means I can even have the atoms touching one another, or they can have spacing much smaller than that of a B. So my spacing along plane B, interplanar spacing along B, is much more scarce or spreaded quite far apart in comparison to my lattice spacing along this particular A direction. But once I bring it to the reciprocal spacing, I can see if I keep my B constant, if I keep my B and represent it in terms of B star, it becomes 1 by my B. So I have this particular thing as 1 by B, and now I can see that in this particular case, in the real lattice, I had A closer to one another, but in diffraction, once I am getting a diffraction pattern, this A has gone much far apart. So this particular 1 by A has become much more sparse or much spread apart. So here I had A less than B. So now what I will get in reciprocal lattice spacing is 1 by A is much greater than my 1 by B. So that is what happens in my reciprocal lattice. This happens in the real lattice. This happens in the other diffraction pattern. I get 1 by A much greater than 1 by B. So that part is being retained in the diffraction pattern. This part I can also see is that the spacing of the rows. This was the spacing of rows in A. This has now become much more farther apart. My spacing of B was this much. So let me use a different color pen so I can show it more clearly that I had something B around this part, and now it has decreased as compared to the A. So in the real space I had A, I had B. In this case I had A less than B, but in this case in the reciprocal or the diffraction pattern, my A dash has increased in comparison to the B dash. So that's what we are able to see from the diffraction of those particular things once I consider only about the rows. Alternately, seeing or following up only with this particular rows or the spacing between the rows, it becomes much more difficult. So sometimes it is necessary that instead of following my rows, I can go back to the particular atoms and take their diffraction pattern. So now I can also follow the position of atoms or the position of planes, and then I can come back to my diffraction pattern. So just tracking the rows or the spacing between the rows, it is sometimes not convenient. So what I'll try to go, with individually atom. So let me come back to 100 plane of a simple cubic, and if I take the real space, I have the vector A1, I have the vector A2, and these are the lattice vector, and they will form a primitive unit cell. If I take a particular box, it will form my primitive unit cell. Now if I come back to my reciprocal lattice, what I can see is my B1 is perpendicular to the A2, or I can also give it by A1 dash. Now my A1 dash is perpendicular to A2. So my A1 was out here, and my now A2 dash, or my A2 dash is now perpendicular to A1. So I can see that my A2 dash is now perpendicular to A1. That part I am seeing out here. And again my A2 is now creating a lattice vector in the reciprocal space which is perpendicular to A2. So now my A1 dash is perpendicular to A2, and I have my A2 dash which is perpendicular to my A1. At the same time I had A1, the distance A1 which is equal to distance A2. So I have this particular unit length, this one was A, this one is also A, and once I come to the reciprocal lattice, I can see that the distances are now similar. So this was forming a square in the real space. It remains that 1 by A is similar out here, 1 by A is also similar in the along the A2 axis. So my A1 dash axis is similar to the A2 dash axis in terms of its magnitude. So I have that it is still forming a particular square. So this particular part I can see. So I have my because in this case I had A is equal to B. So 1 by A remains equal to 1 by B. So that's what I am seeing in the reciprocal space of particular plane of 100 of simple cubic. So in 100 plane of simple cubic, I have the unit cell which has lengths which are constant, which are similar in the two direction. So I have my lattice vector along A side or the x axis, it is equal to A, along y axis is also again equal to B, and A equal to B. So once I take it to the reciprocal lattice spacing, I get vectors which have a magnitude of 1 by A and 1 by B, and since A is equal to B, I get a similar reciprocal space which has again 1 by A is equal to 1 by B. So it forms a diffraction spot which are basically much more periodic, much more similar, and with a similar spacing between the diffraction spots. So along this side my distance is same as along this side in the particular case of simple cubic of 100. Now let me go back to a different way in which we had considered the FCC lattice. So in this particular case, I take a particular FCC cell, I take its 110 particular plane 110, and I can see I have particular atoms which are sitting along this sides. Let me come back to the different color. So I can see that my atoms are located along this particular points. So now what I can see is it is similar to the real space lattice like here. So this is a 110 plane of a FCC, and then what I can see, Along A2 I have much more larger distances as compared to the A1, and this will be the real space unit cell for this particular case. But once I come to reciprocal space, I can track each and every atom like this, or particular row of atoms for a particular plane. What I can see is, now my A1, it has become 1 by A1, and now my A2 has become 1 by A2 dash has become 1 by A2. So now I can see that initially I had this particular magnitude in A2, which is now decreased, and I had now A1 which is now increased. So in this particular case I had A1 which was lesser than A2. In this case I can see my A1 dash is now greater than A2 dash. So that's how it is forming my reciprocal lattice, and the distances are being defined by the original magnitude of the lattice vectors, and again the directionality is also being retained. So I can see the symmetry part is also being retained in the reciprocal space as well, and that thing is again being given in the 111 plane of the FCC. So if I take the 111 plane of the FCC, so that becomes more like this. If I take 111 plane, so that this becomes the 111 plane of the FCC, and in there I can see that I have atoms which are located along the sides. So those are basically located out here, out here, out here, then again on the center of the edges, and if I keep expanding it, I get something which is more like this. Herein I can see that A1 and A2, they are not perpendicular to one another, and they have some lattice vectors that are given along certain directions, certain angles. So I have some value of alpha which is associated now with the real lattice spacing. So but my A1 dash will remain perpendicular to A2. That's what I can see. This is my A2, and now my A1 will now be perpendicular to my A2 direction. So this is my A2, and the A1 dash is now perpendicular to A2, and I had my A1. So now my A2 dash will be perpendicular to A1. So I can see that my A dash 2 is perpendicular to A1, and my A1 dash is perpendicular to A2. That is what the requirement of a reciprocal lattice. And again the spacing part, the spacing is basically same between the between this particular point to this particular point. So from here to here and from here to here, my lattice spacing is the same. So I can see that the space which has been traversed from this particular point to here, or from here this point to here, remains the same. That's what is being shown out here. At the same time, I can see that this particular symmetry is now being retained in the reciprocal lattice as well. So this particular part I can see it is being, I have my this particular point, it has been retained as such. So I can see that the symmetry part is being now retained in the reciprocal lattice, though it has changed by a particular angle, but the symmetry part is now, it is also 6-fold. This also remains the 6-fold symmetry in the reciprocal lattice. So I can see that my real and the reciprocal lattices, they have the same symmetry. So that part is also retained in the reciprocal lattice out here. So all these kind of similarities, I can again show them that A1 and A2 are perpendicular, A1 and A2 dash are perpendicular. At the same time, A1 and A1 dash are parallel in my 110 FCC, but that is not true in the second case, where I have A1 and A2, they are not perpendicular, but A1 and A2 dash are perpendicular, and other way also A2 and A1 dash are perpendicular, but A1 and A1 dash are not parallel. So there can be certain complexities which can generate, but how it retains the symmetry of a particular crystal, that is being given in the reciprocal lattice, that it retains the symmetry of the real lattice. So in certain cases, once we have some surface adsorption, so I can have some matrix which has some adsorption of certain particular other entity, which is again ordered in certain manner. So I can have this adsorbate which has a kind of symmetry in the symmetry of couple of monolayers on the top of a particular matrix, and this is a very common phenomena, because we do see there is some specific adsorption of couple of monolayers on a particular material. So how do they give out a particular diffraction pattern is more like this. The matrix, the overall structure can be divided into the matrix and the adsorbate, which is being adsorbed on the surface. So for a particular matrix, I can see my length is A1, A2. I can take it back to A-1 and A-2 in the reciprocal lattice. This is the real lattice. So I can take it to the reciprocal lattice. This is a reciprocal lattice. I can see that this particular part gives me certain diffraction pattern, and then in the second case I have my B1 and B2, which are much greater than, which are twice the A1, and my B2 is also twice the A2. So from construction I can see it from here. So I can see that my B1 is equal to 2 times A1, B2 is equal to 2 times A2. So what happens in the reciprocal lattice is my B1 becomes half of that and my B2 becomes half of that. So what I get? For this I get much more diffraction spots as compared to my first case. So I will see that my diffraction spots are much more in number once I have an adsorbate which is spreaded much more scarcely as compared to my overall matrix. But the problem is I have so less number of adsorbate on the surface of a matrix that its intensity might not be that great, but they will be overlapped with over one another. So if I combine this and this, I get something which is this. So what I am seeing here is I am combining this part, the diffraction pattern which is coming out from the matrix, I am combining it with the diffraction pattern which is coming out from the adsorbate, and then what I get finally is a combined diffraction pattern. And I can see I have a dark spots which is coming basically from the matrix out here, and then I have also some overlapping of these particular points which are coming from the adsorbate. This is from the adsorbate. There is some overlapping of these points even at this particular points. So I can see those things, particular things, that I have a kind of combination between the my matrix, the diffraction spots which are coming from the matrix, diffraction spots which are coming from only from the adsorbate, but at the same time it is not telling anything about the intensity of the diffraction spot. So I don't know what will their intensity will be, but I can predict that this adsorbate spots will be weaker because they are fewer in number. The diffraction spot which will, the intensity with which they will come out will be much more feeble. So I can see that I can overlap all these particular intensity points in one because I have a combination of these two, and so I can combine them to find out what eventually the diffraction pattern will look like. So in summary, we can say that to eliminate the complexity of representing a particular real crystal, the diffraction occurs when the evolved sphere touches my reciprocal lattice planes, and reciprocal lattice can be given by a set of parallel planes with an and all those planes can be represented by a single point. So I know their magnitude is equal to 1 by the inverse of the reciprocal of the interplanar spacing. So in reciprocal lattice, what I am getting is a point which represents a plane, and the magnitude of that particular point from the origin is equal to the 1 by the interplanar spacing between the planes which it represents. So that's how I can spread it around, and I can open it up, because if I take a real crystal, all the points, all the planes tend to agglomerate at the origin. So there is much more segregation of all the planes if I start representing each and every plane. So in reciprocal lattice, I am more or less like opening it up, so I can see a much more periodic way of representing all the planes, all the set of parallel planes, and I can define the direction. I can define the magnitude. The magnitude is equal to 1 by d, where d is the interplanar spacing. So I can, in reciprocal space, it will become 1 by d, and I can also find their zone axis. I can also find the overall magnitude and direction of all those planes. So that eventually tells me how the diffraction spots will appear once the particular material is getting diffracted. So it is a construction or the merger of the evolved sphere, and how it basically coincides with the lattice points, the reciprocal lattice points, to give me to obey the Bragg's law and give me a diffraction spot. Again, Bragg's law is a negative law, so even when the Bragg's law is being satisfied, it may not give a diffraction spot depending on what is the overall scattering factor and how it is basically getting merged into, or what is the intensity of that particular point. So I may not even get a diffraction spot. And also we learned about how different planes can have how different planes can basically provide a kind of a reciprocal lattice, and how we can either go about following the row or the spacing between the rows, or we can go with individual atoms which can get constructed back into the reciprocal lattice. We also saw how we can combine if we have more than one particular matrix, and how can we combine them to form a set of reciprocal lattice, and it also maintains the symmetry of the real crystal. So that is the advantage with the reciprocal lattice, and it can accommodate wide variety, whether we have axes A1 or A2, whether they are parallel or not, whether they are perpendicular or not. We can always grab it back into the reciprocal lattice, and the axes are perpendicular to the other two or other one axis, which basically defines a particular unit cell. So that is what we learnt about the reciprocal lattice. I end my lecture here. Thanks a lot.